We're going to talk a little bit about exponential growth and decay word problems. These are broken down into different categories to kind of help you as a refresher. When you're working on other problems, you can go back and look at them for examples. So copy these down so you have them for examples. Really try to understand the concept of what's happening. Please ask any questions if you do not understand afterwards. So the first one is on compound interest. Remember that annually means once per year. So for this particular one, you want to start a savings account and you will put in $3,800 to start. You will then earn 1.8% interest per year. How much will you have in 15 years? So we think about this as compound interest. We know that we have a starting amount of $3,800. So we're going to work with $3,800 as our initial. So think about our formula as y equals a times b to the x. So in this particular case, $3,800 at our start, we have to think about when we put this start in, we have 100% of that, and that amount is growing 1.8% interest annually. So we think about 100% of what we have plus the 1.8% that we're growing, and we have it growing exponentially, and that x we'll talk about in just a minute. So we want to think about changing this 100% to a number. I can't use percentages in here, so we're going to change it by just moving it decimals. So this actually is 1 plus, and then we move this one to decimals as well, 0.018 or 18 thousandths. This gets added together, and we end up with 3,800 still as our starting point, and then 1.018 or 1 and 18 thousandths, and then we want to talk about 15 years. So our x becomes 15 because that's how many years, how many annual years it's happening, so 15. Then we're going to use our calculations for this amount, and then we would get, in your calculator, you take this first to the 15th power, then multiply it times 3,800, and you're going to see your answer will be $4,965.93. This one we're going to do compound interest, but notice that I have a note for you. Quarterly means 4 times per year. So in this case, we're going to use a quarterly growth or amount that we're earning. So we start in this one with $1,500, and we're going to earn 6.5% quarterly. And we want to know what our balance will be in our bank account in 18 years. If we don't ever touch it, what kind of money will we have in 18 years? So we're going to think about y equals a b to the x, and our initial, of course, here is going to be our 1,500. We have to think again, we're talking about percentages, so we have 100%, which we know is 1, our whole amount, plus we're going to have 6.5%, but this time we have it quarterly. So that's split into 4 pieces, and we would have a little unknown up here, our exponential. So now we're going to think about changing this percentage into a decimal. So if you change this to 2 over, you get 0.065 or 65 thousandths, and divided by 4, you're going to end up with 1 point, this amount here turns into 0.1625. So that is just changing this percentage here into this percent part into, divided by 4, into this decimal. So then we're going to look at how then that would calculate with our $1,500 starting. So this is all of our y equals our total amount. And in this case, we're talking about 18 years. Well, you have to think we're talking quarterly. We need to know how many quarters or how many quarterly periods are in 18 years. So think about seasons when you think about quarterly. Winter, spring, summer, fall. It's every so many months. So we're talking about quarters. Well, for our particular case, we're talking about 18, and we know that there's 4 quarters in each year. So we have to do 18 times 4 to get our true number. This was our 18 years, and we know there's 4 quarters. And we're going to end up with 1,500 times 1.01625 raised to the 72. And then when we work our calculations out, our Y, or our amount that we're going to have in our bank without touching anything, is $4,787.75. So we grew quite a bit of money by not touching anything at 6.5% quarterly. This is another example of change over time. We still have a percentage in here, but it doesn't give us some explicit information we have to think about. So in 1985, the cost of hospital care was increased, since then has increased 8.1% per year. In 1985, the cost was $460 per day. What is the approximate cost per day in 2000? So we don't think about what our time frame is. We have to look at 1985 to 2000. Well, that's a difference of 15 years. So that's going to be important for our exponent amount, for our exponential x value. So we have to know that. So we have to think about that. It's not explicitly written. So when we start, we have y is equal to a, b to the x. Our initial amount, originally what we're talking about, is $460 per day. So that's what it was originally. So that is our initial amount. We then think about anytime we see percentage, we have to think about we had a whole that we paid, so the whole 460, and then it increased over top of that 8.1%, in this case per year. So that's like an annually. So that would be plus 8.1%. Well, we know we can't leave it as a percent, so we change this to a decimal. So we end up with 1 plus 0.081, and then we just simplify that down to 1.081 total because we added them together. So our initial is still 460. Now we know that our 15 years goes here in our exponent. So we put our 15 here. And then we're going to calculate 1 and 81 thousandths to the 15th power, and then times 460. So we have y is equal to $1,479.60. So in the year 2000, that was the average daily cost for hospital care. We could continue that on if I wanted to know in 2019 what it would be. Then I have to think about from 1985 to now, how many years would that be? And that's 34 years. So the biggest difference would be that if in 2019, if I wanted to know, my formula would then be y equals 460 as my initial, and then still the same growth factor. Excuse me. But now I would have an exponent of 34 years. So then that would be $6,498.77 per day. I haven't been to the hospital recently, but I know that medical care is very expensive, so hopefully it's not that much. But this is an example of change over time if it was a set increase of 8.1%. In the real world, things fluctuate, but this kind of gives us an overall generalized view. So we're going to talk about half-life. You will hear this word half-life and think about when you hear that as decay. So this is a certain type of radiation that is being used to treat a patient with cancer. The patient receives 12 millicurie, which is abbreviated as MCI, and that is what is given to them at their visit. And the half-life of this medicine is 8 days. So think about as they take it, every 8 days, it cuts into half. It goes down half. So what's in their body is half left, half left. And so we want to know how much radiation medication will be left in their body after 16 days. So we still are using our formula of y equals a, b to the x. And in this case, we know it's half-life, so we know that our growth factor or common ratio is going to be a smaller number than 1. So our initial amount we start with is the 12. That's what they were given. We know that our growth of decay or decay factor is a half because it's half-life. And in this case, we have to do a little bit of calculation here. In 16 days, we need to know how many half-lives occurred. Well, if each half-life is 8 days, how many times is 8 going to 16? Well, that's 2. So then we're talking about a 2. So when we put this into our calculator, a half raised to the second power, then times 12, the patient would have 3 millicurie of radiation left in their body. So exponential decay, we know we are getting smaller. This one with the percent, we have to think about, just like we did with compound interest or growing, our decay, our decrease, if there's a percent, we have to think of 100% minus the percent we're actually decreasing. So if it was decreasing 5%, we would actually take that away from 100, and we would use 95 in our growth area, in our decay area, or common ratio area of our formula. So in this one, in 1980, the number of gallons of whole milk each person in the U.S. drinks decreased by 4.1% each year. In 1980, each person drank 16.5 gallons of whole milk per person. What is the average gallons consumed in the year 2000? So our initial amount, our A, is going to be our 16.5. That's what it was in 1980. And now we're talking about 2000. So we got to think about how long is that span of time? Well, that's 20 years. So that's going to help us know what to put for our X. Then we have to think of our 4.1%. This is a decrease. So we have to think of 100% minus 4.1% as our growth factor, or decay factor in this situation. So when we take 100 minus 4.1, we end up with 95.9%. Well, we don't want to have 95.9%. We have to change it to a decimal. So then this is going to be what our B is. So Y is equal to our initial of 16.5 times 959 thousandths. And we're going to raise it to the 20th because we're talking about 20 years. So when we work this out, we end up with 7.14 gallons. So in the year 2000, the average that milk that people drank, whole milk, was 7.14 gallons per year. This problem's comparing two situations. So Company A pays $10,000 the first month you work there, and then each month the pay will increase by $5,000. Company B pays $500 the first month, and each month after the pay will double. In which month will Company B exceed, in money, Company A? So one thing we have to remember, some important things here. If we don't start at 0 months, meaning in this case we started at month 1, we actually got something at month 1, we have to take that into account with our exponent. If we start at 0, remember when x is 0, that's our starting point, then we know that we can adjust from there. So I'm going to make a little chart to help you kind of see this visually and see how you can actually use it as a the equation. All right, so here's a table that I made. Notice we start at 1 month, and I just went down to 8 months. Company A, we got $10,000 the first month, and then increased every month by $5,000. So if we think about what's happening, every time we go up, this is adding $5,000 to our initial amount. This is actually a linear problem. This is not exponential. So it's increasing at a fixed amount every month. If it's increasing or decreasing at a fixed amount every month, that tells us it's linear. So that's something we need to remember. However, the Company B gets $500 the first month, and then it doubles every month after. So 500 became 1,000, 1,000 became 2, 2 became 4. I don't know what job this is, but I'd love to have it. And so every time the month after, we get double what we got the month before. So we know that if we're doubling, our growth factor is actually 2. Now, because we started at month 1 and not x being 0, we have to think about changing our equation just a tad. So our normal y equals ab to the x is if we start, our x has to be exactly at the number we're looking for. Well, in this case, our initial amount is 500, but it's not at month 0. It's at month 1. It's after we've worked that month. So we have y is equal to 500, which is our initial amount, but we have to take into account our differences for our x. So if it's doubling, we know our growth factor is 2. Here, however, we would have x, what we need to find, but minus 1, because we did not start at 0 for 0 months. We actually started at 1. So we have to take that into account. So if we wanted to know, for example, what it would be at month 8, if we plugged in 8 here, it's actually 500 to the power, or to the growth factor of 2, and then 8 minus 1, which actually is to the 7th power. So when we put it in our calculator, we're actually looking for this 8th month amount, and if you put it in the calculator as just 8, you're not going to get 64,000. If you put it in the calculator as 7, you do get 64,000. So this minus 1 has to take into account that we have to make some adjustments when we do not start our months or years or days at 0. We actually start at something else, like 1 month in, 2 months in, a year in, and so forth. So our question asks us, what month will we first, or how many months will we first exceed, Company B exceed Company A? And we can see it's going to be in month 8, because month 7, we were still at 32,000 in Company B, and it was 40,000 in Company A. So you'd have to work there for at least 8 months to see a difference, a large enough difference in that company. I definitely would go with Company B if I had to choose that for a job. So some last reminders. When you're increasing or decreasing with a percent, think exponential. You do have to change those percents. Think about the 100 or take it away for 100% and make those adjustments. Same thing, you have to think about those things with annual or compounded annually or quarterly or even monthly. That would change a little bit with the time. And if you're increasing or decreasing with a fixed amount, it's always linear. So don't get the two confused. They're really tricky with wording sometimes, so you've got to really be careful. All right, go to your other page to see now what you're understanding.